Hello students, today we are going to discuss class 11 chemistry chapter number 3, classification of elements and periodicity in properties. You can see this periodic table organization as alkali metals, alkaline, noble gases, transition metals. The periodic table and the elements. What is the periodic table? What information is obtained from the table? How can elemental properties be predicted based on the periodic table? Early attempts at classification of elements. The earliest attempt to classify elements was grouping then known elements, about 30 elements, into the two groups called metal and non-metal. Metal and non-metals. The defect in this classification was that it had no place for metalloids, elements which have properties of both metal and non-metal, which were discovered later. So the classification of elements, as more elements were discovered, the study of elements and their properties and also their classification became very alive in the scientific world. So many scientists were trying to study the characters of elements were known and made an attempt to classify according to their characters. So now you can see this periodic classification of elements. The classification of elements, the arrangement of elements into the different groups on the basis of the similarities in the properties is called classification of elements. The classification of similar elements into groups make the classification to study the elements easier. There are 114 different elements known so far. In the periodic table you will see there are total 118, but total found yet now is 114, till 4 of the elements are yet to found. Early attempts at classification of elements was grouping the known elements, about 30 elements, into the two groups called metal and non-metals, and the defect in this classification was that it had no place for metalloids, elements which have properties of both metals and non-metals, which were discovered later. As you can see, the 4 scientists which had played the main role to form the periodic classification of elements. The first was Dobrynin, then Newlands, Mendeleev, Niels Bohr. These were the main who had given some laws like Dobrynin Trade's law, Mendeleev's periodic table law, Newlands octave law, Niels Bohr's long form of the periodic table law, then Moseley's, and many more. Just let's go ahead. You can see here as the classifications. You can see in this picture very clearly Dobrynin's law of trades, Newland's law of octaves, and Mendeleev periodic law was the periodic classification of elements. H.G.J. Moseley modern periodic law, Niels Bohr long form of the periodic table, and 18 groups and 17 periods. Means it was generally divided into the two parts, that how the scientists have discovered these periodic tables. According to Dobrynin Trade's law, he had given that elements must be arranged according to 3-3, means first and third elements atomic weight average will be the second element's atomic mass. You can see here lithium atomic weight was 7, potassium 39. So 7 plus 39 by 2, that is equal to 46 by 2, that is 23. 23 the atomic mass of sodium. So as he had seen that this rule is followed, but as he had gone ahead, so he has seen that this laws is not comfortable for all the elements, as he had found chlorine, bromine and iodine. So there was a difference. It was not accurate. Similarly, he had found in calcium, strontium and barium. Again, it was different. It was not accurate. So his laws was not comfortable according to periodic table. Now, in the universe, total 115 elements have been discovered till today. Each of these elements possesses different properties. It is difficult to understand and use the properties of each element at a time. Hence, attempts were made to discover ways to learn the properties of elements in systematic order. In 1829 to 1830, plus 30 plus elements were known. Dobryner, a German scientist, made some groups of 3 elements each and called them a traits, that is known as Dobryner traits law. Atomic mass of the second element of traits is nearly equal to the arithmetic mean of atomic mass of the other 2 elements. Elements in a trait have similar lithium, sodium, potassium. Only these 3 elements had followed the rule. It is found that the atomic mass of sodium is the arithmetic mean of the first element, lithium, and the third element, potassium, and the properties of sodium were mean of properties of that of lithium and potassium. And next you can see the Dobryner, means after the Dobryner, Newland's octave rules, as he had given each and every 8th element have the similar properties. So he had arranged the elements as hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, sodium, magnesium. Yet the inert gas were not discovered, so these laws were comfortable and it has been applied. But later on, as the inert gas were discovered, that time his laws were failed. After then, Dmitri Mendeleev. In 1869, Mendeleev and Lothar Meyer from Germany published nearly identical classification schemes for elements known to date. The periodic table is based on the similarity of properties and reactivities exhibited by certain elements. Later, Henry Moseley from England between 1887 to 1915 established that each element has a unique atomic number, which is how the current periodic table is organized. Original table by Mendeleev classified elements in horizontal rows based on their atomic mass. When there was a repeat of properties, the elements were placed in the next row. Concluded that similar properties appear at regular intervals when the elements are listed in order of increasing atomic mass. Mendeleev's periodic law. The properties of elements are periodic functions of their atomic masses. Examined relationship of atomic mass and physical and chemical properties of elements. Chemical properties considered the compounds formed by elements with hydrogen and oxygen, as these two were very reactive, forming compounds with most of the known elements like hydrides and oxides. He arranged the 63 known elements into 6 horizontal periods and into 8 vertical groups. Periods based on increasing atomic mass and groups based on similarity in properties. Mendeleev arranged the elements in the periodic table ordered by atomic weight or mass. He arranged the elements in periods and group in order of the increasing atomic weight. He placed the elements with similar properties in the same group. However, he did not stick to the arrangement for long. He found out that if the elements were arranged strictly in order of their increasing atomic weights, then some of the elements did not fit within the scheme of classification. Therefore, he ignored the order of atomic weights in some cases. For example, the atomic weight of iodine is lower than the atomic weight of tellurium. Still, Mendeleev placed tellurium in group 6 before iodine in group 7, simply because iodine properties are so similar to fluorine, chlorine and bromine. This is the periodic properties, periodic table, group periods, periodic table, ionization energy, electron affinity, electron negativity, radii, lengthenite contractions, and metallic character. The trends in physical properties, we will study about the atomic radius, ionic radius, ionization enthalpy, electron gain enthalpy, electron negativity, oxidation states, and chemical reactivity. As the arrows are shown, atomic radii or atomic radius increases in groups from top to bottom as it gets more energy level, more shell, more orbit, so the atomic radii increases from top to bottom, and atomic radius decreases from left to right in the periods, or you can say it increases from right to left in the periods. Ionization and energy increases from left to right in the period. Electron affinity increases from left to right in the period. Non-metallic character increases from left to right in the period. Metallic character decreases from left to right in the period. Electron affinity decreases from top to bottom in the groups. Ionization energy decreases from top to bottom in the groups. As you can see here, the metals, semi-metals, and metalloids. Semi-metals means metalloids and non-metals. Periodic table trends. According to the trends, atomic radius, electron affinity, ionization energy, electron negativity, how it increases and decreases in period and groups. You can take a screenshot. As to remember the summary of trends, as I have written, electronegativity increases from left to right in period, ionization energy increases from left to right in a period, atomic radius decreases from left to right in a period, nuclear charge increases from left to right in a period, shielding effects is constant from left to right in a period. Electronegativity decreases from top to bottom in a group, ionization energy decreases from top to bottom in a group, atomic radii increases from top to bottom in a group, nuclear charge increases from top to bottom in a group, shielding effect increases from top to bottom in a group. As if anybody asks you what are the family members' name, so you can see alkali, alkaline, chalcogen, halogen, noble gas, transition metals, inner transition elements, as it have been found. The time, the name of the groups were like this: alkali, earth metals, alkaline earth metals, transition metals. Group 6 or 16, 6th A or 16, chalcogen, 17th A, halogen, 18th noble gas, 13 boron family, 14 carbon family, 15 nitrogen family. These were the names of groups. Electronic configuration from the periodic table, you can see NS1, NS2, NS2, ND1 to NS2, ND10, NP1, NS2, NP1, NS2, NP2 to NS2, NP6, were the general electronic configuration of a periodic table. Metals, metalloids, non-metals. Metals divided into the three groups: alkali, alkaline, and transition. Non-metals divided into the three groups: noble gas, halogens, and chalcogens. Trends in atomic radius. The atomic radius of an element is a measure of the size of its atom, usually the distance from the nucleus to the boundary of the surrounding cloud of electrons. Trends in ionization energy. The energy required to remove the valence electron from the atomic space. Trends in electron affinity. Electron affinity is a measure of the energy that is released when an atom acquires an electron. we say that the more energy is released, the more readily the atom becomes an anion. This is the summary of the trained periodic table. A chemical element is a species of atoms having the same number of protons in their atomic nuclei, that is the same number of atomic number, or Z. 118 elements are identified, out of which 94 occurs naturally on Earth, with the remaining 24 being synthetic elements. There are 80 elements that have at least one stable isotopes and 38 that have exclusively radionuclides, which decay over time into the other elements. Iron is the most abundant element by mass, making up Earth, while oxygen is the most common element in the Earth crust. Chemical elements constitute all of the ordinary matter of the universe. However, astronomical observation suggests that ordinary observable matter makes up only about 15% of the matter in the universe. The remainder is dark matter. The composition of this unknown, but it is not composed of chemical elements. The two lightest elements, hydrogen and helium, were mostly formed in the Big Bang and are the most common elements in the lithium. This hydrogen and helium are the most common elements in the universe, and the next three elements, lithium, beryllium and boron, were formed mostly by cosmic rays spallitations and are thus rarer than behavior elements. Formation of elements with from 6 to 26 protons occurred and continuously to occur in main sequence stars via stellar nucleosynthesis. The high abundance of oxygen, silicon and iron on Earth reflects their common production in such stars. Elements with greater than 26 protons are formed by supernova nucleosynthesis in supernovae, which when are explode blast these elements as supernova remands for into the space, where they may become incorporated into the planets when they are formed. The term element is used for atoms with a given number of protons, regardless of whether or not they are ionized or chemically bonded, as for example hydrogen in water, as well as for pure chemical substances consisting of a single element, that is hydrogen gas. For the second meaning, the term elementary substance and the simple substances have been suggested, but they have not gained much acceptance in English chemical literature, whereas in some other languages their equivalent is widely used, that is French crop, similarly Russian and pokmin. A single element can form multiple substances different in their structure. They are called allotropes of the elements. When different elements are chemically combined with the atoms held together by chemical bonds, they form chemical compounds. Only a minority of elements are found uncombined as relatively pure minerals. Among the more common of such native elements are copper, silver, gold, carbon, as coal, graphite or diamonds, and sulfur. All but a few of the most inert elements such as noble gases and noble metals are usually found on the earth in chemically combined form as chemical compounds, while about the 32 of the chemical elements occur on the earth in native uncombined forms. Most of these occurs as a mixtures. For example, atmospheric air is primarily a mixture of nitrogen, oxygen and argon, and the native solid elements occur in alloys such as that of iron and nickel. The history of the discovery and the uses of these elements began with primitive human societies that found native elements like carbon, sulfur, copper and gold. Later civilization extracted elements copper, tin, lead and iron from their ores by smelting using the charcoal. Alchemists and chemists subsequently identified many more. Almost all the naturally occurring elements were known by 1900. The properties of the chemical elements are summarized in the periodic table, which organizes the elements by increasing atomic number into the rows called periods, in which the columns called groups share the recurring periodic physical and chemical properties. Save for unstable radioactive elements with short half-lives, all of the elements were available industrially, most of them in low degree of impurities. Atomic number. The atomic number of an element is equal to the number of protons in each atom and defines the element. For example, all carbon atoms have or contain 6 protons in their atomic nucleus, so the atomic number of carbon is 6. Carbon atoms may have different number of neutrons. Atoms of the same element having different number of neutrons are known as isotopes of the elements. The number of protons in the atomic nucleus also determines its electric charge, which in turn determines the number of electrons of the atom in its non-ionized state. The electrons are placed into atomic orbitals that determines the atom's various chemical properties. The number of neutrons in a nucleus usually has very little effect on an element's chemical properties, except in the case of hydrogen and deuterium. Thus, all carbon isotopes have nearly identical chemical properties because they all have 6 protons and 6 electrons. Even though carbon atoms may, for example, have 6 or 8 neutrons, that is why the atomic number rather than mass number or atomic weight is considered the identifying characteristic of a chemical element. The symbol for atomic number is capital Z. Isotopes. Isotopes are atoms of the same element, that is with the same number of protons in their atomic nucleus but having different numbers of neutrons. Thus, for example, there are 3 main isotopes of carbon. All the carbon atoms have 6 protons in the nucleus, but they can have either 6, 7 or 8 neutrons. Since the mass number of these are 12, 13 and 14 respectively, the 3 isotopes of carbon are known as carbon 12, carbon 13 and carbon 14. Often abbreviated to carbon 12, carbon 13 and carbon 14. Carbon in everyday life and in chemistry is a mixture of carbon 12 about 98.9%, carbon 13 about 1.1% and about 1 atom per trillion of carbon 14. Most 66 of 94 natural occurring elements have more than 1 stable isotopes, except for the isotopes of hydrogen, which differ greatly from each other in relative mass, enough to cause chemical effects. The isotopes of a given element are chemically nearly indistinguishable. All of the elements have some isotopes that are radioactive, that are called radioisotopes, although not all of the radioisotopes occur naturally. The radioisotopes typically decay into other elements upon radiating an alpha or beta particle. If an element has isotopes that are not radioactive, these are termed stable isotopes. All of the known stable isotopes occur naturally. See primordial isotopes. The many radioisotopes that are not found in nature have been characterized after being artificially made. Certain elements have no stable isotopes and are composed only of the radioisotopes. Specifically, the elements without any stable isotopes are technetium, atomic number 43, promethium, atomic number 61, and all absorbed elements with atomic number greater than 82. So the 80 elements with at least 1 stable isotopes, 26 have only 1 single stable isotopes. The mean number of stable isotopes for the 80 stable elements is 3.1 stable isotopes per element. The largest number of stable isotopes that occur for a single element is 10, 14, element 50. Isotopic mass and atomic mass. The mass number of an element A is the number of nucleons, protons and neutrons in the atomic nucleus. Different isotopes of a given element are distinguished by their mass numbers, which are conventionally written as a superscript of the left hand side of the atomic symbol, as for example uranium U38. The mass number is always a whole number and has unit of nucleons. For example, magnesium 24. 24 is the mass number of an atom with 25 nucleons, 12 protons and 12 neutrons. Whereas the mass number simply counts the total number of neutrons and protons and is thus a natural or a whole number. The atomic mass of a single atom is real number, giving the mass of a particular isotope or nuclide of the element expressed in atomic mass or units. In general, the mass number of a given nuclide differ in value slightly from its atomic mass, since the mass of each proton and neutron is not exactly 1 unit, since the electrons contribute a lesser share to the atomic mass as neutron number exceeds proton number, and finally because of the nuclear binding energy. For example, the atomic mass of chlorine 35 to 5 significant digit 34.969 unit, and that of chlorine 37 is 36.966 unit. However, the atomic mass in unit of each isotope is quite closer to its simple mass number, always within 1%. The only isotope whose atomic mass is exactly a natural number is carbon 12, which by definition has a mass of exactly 12 because unit is defined as 1 by 12 of the mass of a free neutral carbon 12 atom in the ground state. The standard atomic weight, commonly called atomic weight of an element, is the average of the atomic masses of all the chemical elements, isotopes, as found in the particular environment, weighted by isotopic abundance or relative to the atomic mass unit. This number may be a fraction that is not close to a whole number. For example, the relative atomic mass of chlorine is 35.453 unit, which differs greatly from a whole number, as it is an average of about 76% of chlorine 35 and 24% of chlorine 37. Whenever a relative atomic mass value differs by more than 1% from a whole number, it is due to this averaging effects, as significant amounts of more than one isotope naturally present in a sample of that element. Chemically pure and isotopically pure. Chemically pure and isotopically pure. Chemists and nuclear scientists have different definitions of a pure element. In chemistry, a pure element means a substance whose atoms all, or in practice almost all, have the same atomic number or number of protons. Nuclear scientists, however, define a pure element as one that consists of only one stable isotope. For example, a copper wire is 99.99% chemically pure if 99.99% of its atoms are copper with 29 protons each. However, it is not isotopically pure since ordinary copper consists of two stable isotopes, 69% of 63 mass of copper and 31% of 65 isotopes of copper. With a different number of neutrons, however, a pure gold ingot would be both chemically and isotopically pure, since ordinary gold consists only of one isotope, that is Uranum-197. Allotropes, atoms of chemically pure elements, may bond to each other chemically in more than one way, allowing the pure elements to exist in multiple chemical structures called spatial arrangement of atoms, known as allotropes, which differ in their properties. For example, carbon can be found as diamond, which has a tetrahedral structure around each carbon atom, graphite, which has layers of carbon atoms with a hexagonal structure stacked on top of each other, graphene, which is a single layer of graphite that is very strong, fluorescents, which have nearly spherical spaces, and carbon nanotubes, which are tubes with a hexagonal structure. Even these may differ from each other in electrical properties. The ability of an element to exist in one of many structural forms is known as allotropy. The standard state, also known as reference state of an element, is defined by as its thermodynamically most stable state at a pressure of 1 bar and a given temperature, typically at 298.15 Kelvin. In thermochemistry, an element is defined to have an enthalpy of formation of 0 in its stable state. For example, the reference state for carbon in graphite, because the structure of graphite is more stable than that of the other allotropes. Properties. Several kinds of descriptive categorizations can be applied broadly to the elements, including consideration of their general physical and chemical properties, their states of matter under familiar conditions, their melting and boiling points, their densities, their crystal structures as solid, and their origins. General properties. Several terms are commonly used to characterize the general physical and chemical properties of the chemical elements. A first distinction is between the metal which readily conduct electricity, nonmetals which do not, and a small group, the metalloids, having intermediate properties and often behaving as semiconductor. A more refined classification is often shown in colored presentation of the periodic table. This system restricts the terms metals and nonmetals to only certain of the more broadly defined metals and nonmetals, adding additional term for certain sets of the more broadly viewed metals and nonmetals. Presently here includes actinides, alkali metals, alkaline earth metals, halogens, lanthanides, transition metals, post-transition metals, metalloids, polyatomic nonmetals, diatomic nonmetals, and noble gases. In this system, the alkali metal, alkaline earth metal, and transition metals, as well as the lanthanides and the actinides, are the special group of the metals viewed in a broader sense. Similarly, the polyatomic nonmetals, diatomic nonmetals, and the noble gases are nonmetals viewed in the broader sense. In some presentations, the halogens are not distinguished, with astatine identifies as a metalloid and the other identify as nonmetals. States of matter. Another commonly used basic distinctions among the elements is their states of matter, called phase, whether solid, liquid, or gas, at a selected standard temperature and pressure called STP. Most of the elements are solids at conventional temperature and atmospheric pressure, while several are gases. Only bromine and mercury are liquids at 0 degrees Celsius, that is 32 degrees Fahrenheit, and the normal atmospheric pressure. Cesium and gallium are solids at the temperature but melts at 28.4 degrees Celsius, that is 83.2 degrees Fahrenheit, and 29.8 degrees Celsius, that is 85.6 degrees Fahrenheit, respectively. Melting and boiling points. Melting and boiling points, typically expressed in degrees Celsius at a pressure of 1 atmosphere, are commonly used in characterizing the various elements. While known for the most elements, either or both of them measurements is still undetermined for some of the radioactive elements available in only tiny quantities. Since helium remains a liquid even at absolute zero at atmospheric pressure, it has only a boiling point and not a melting point in conventional presentations. Densities. The density at a selected standard temperature and pressure called STP is frequently used in characterizing the elements. Density is often expressed in grams per cubic centimeter, G upon cm cube. Since several elements are gases at commonly encountered temperatures, the density are usually stated for their gaseous forms. When liquefied or solidified, the gaseous elements have densities similar to those of the other elements. When an element has allotropes with different densities, one representative allotrope is typically selected in summary presentation, while densities for each allotrope can be started where more detail is provided. For example, the three familiar allotropes of carbon, amorphous carbon, graphite, and diamond, have densities of 1.8 to 2.1, 2.267, and 3.515 gram per centimeter cube respectively. Crystal structure. The elements studied to date as solid samples have 8 kinds of crystal structure: cubic, body-centered cubic, face-centered cubic, hexagonal, monoclinic, orthorhombic, rhombohedral, and tetragonal. for some of the synthetically produced transuranic elements, available samples have been too small to determine crystal structures. Occurrence and origin of Earth. Chemical elements may also be categorized by their origin on Earth, with the first 94 considered naturally occurring, while those with atomic numbers beyond 94 have only been produced artificially as the synthetic products of man-made nuclear reactions. Of the 94 natural occurring elements, 84 are considered as primordial and either stable or weakly radioactive. Shots for them to have been represented at the beginning of the solar system and are therefore considered transient element. Plutonium is usually also considered as a transient element because primordial plutonium has by now decayed to almost undetectable traces. Of these 10 transient elements, polonium, radon, radium, actinium, and protactinium are relatively common decay products of thorium, uranium, and plutonium. The remaining 6 transient elements, tactinium, promethium, astatine, francium, and neptunium, and plutonium, occurs only rarely as the products of rare decay modes of nuclear reaction processes involving uranium or other heavy elements. Elements with atomic number 1, though 40 are stable, which those with atomic number 41 through 82 except tactinium and promethium are metastable. The half-lives of these metastable theoretical radionuclides are so long, at least 100 million times longer than the estimated age of the universe, that their radioactive decay has yet to be detected by experiment. Elements with atomic number 83 through 94 are unstable to the point that the radioactive decay can be detected. 3 of these elements, bismuth, thorium, and uranium, have one or more isotopes with half-lives long enough to survive as remnants of the explosive stellar nucleosynthesis that produced the heavy element before the formation of our solar system. For example, at over 1.9 into 10 to the power 19 years, over a billion times longer than the current estimated age of the universe. Bismuth 209 has the longest known alpha decay half-life of a naturally occurring element. The very heaviest 24 elements, those beyond plutonium element 94, undergoes radioactive decay with short half-lives and cannot be produced as daughters of longer-lived elements, and thus they do not occur in nature at all. Don't forget to like and subscribe the channel. Thank you very much.